back to data mining. Let's talk about where to split a decision tree. In this module, we will discuss attribute selection issues, and we will learn how to optimize attribute selection by hand. For that, we will compute the Gini index, and we will compute the information gain on a classification tree. But first, let's consider some important attribute selection issues. One of the biggest conundrums in generating a decision tree is to find the optimal split attribute, that is, the attribute on which to split the tree at every level of the hierarchy. We want to find attributes that lead to a clear, unequivocal class membership. So here, for example, that is the combination of age and student that allows us to accurately predict our bias computer value, either with no or with yes. And that attribute changes for our over 40 category, in which we combine age and credit rating. That allows us to accurately predict bias computer no and bias computer yes. There are two major methods and others that are derived from them that help us find the optimal split attribute in a decision tree. The first one's called the Gini index, and then we also have information gain. The Gini index measures the probability of a particular variable being wrongly classified when it is randomly chosen. Since we're dealing with probability, we're also dealing with numbers between 0 and 1, where 0 or any number close to 0 indicates that all elements have been correctly classified. In Gini index language, that's also called 100% purity. And 1 means that elements have been randomly classified. Now, as you can already tell, for Gini index, smaller is better. Information gain is a little bit different. Information gain calculates the difference between the original information requirement, just based on the proportion of classes, and then the extra information that is gained by introducing a new split attribute. That information gain is measured in bits, and because we're talking about information gain, you can already tell that bigger is better. Let's talk about the Gini index and look at an example. The Gini index is based on the concept of purity. Purity means that a node is 100% impure when a node is split evenly 50-50, and it is 100% pure when all of its data belongs to a single class. So the goal for the Gini index is to reach maximum purity and avoid impurity. Let's see what that looks like. All right, so let's get started calculating the Gini index. This is the Gini index formula here. So we are looking for the probability, pi here, of an object in our data set being assigned to a particular class. And then we're going to sum up all of these probabilities after we've squared them. And we're going to subtract that from 1. So the bigger our probability is here, our pi squared, the lower the overall Gini index is, because then this number here will be bigger when we subtract it from 1. Let's see how this plays out in the data set that we're looking at. We have age, income, student, and credit rating, and we're looking at their effect on our bias computer class attribute. So first, we are going to look at the overall distribution in our class attribute. So our bias computer equal to yes gives us 9 out of 14 records. Our bias computer no gives us 5 out of 14 records. Well, now we have the probabilities and we can plug them into this formula. So we have 1 minus, and then we have 9 out of 14 squared minus 5 out of 14 squared, and that gives us a Gini index that we're starting with of 0.459. Not the best, but all this tells us is that bias computer is, well, it's a class attribute. All right, so let's calculate the Gini index for our income attribute. Our income attribute partitions our data space into 10 elements in our low-medium category. We'll call that D1, and 4 elements in our high category. We'll call that D2. So we're setting up our equation now for the Gini index for income as an element of low and medium for our data space, and that gives us 10 over 14 multiplied by the Gini index for our data space D1, and 4 over 14 multiplied by our Gini index for our data space 2. That is our high. So here we have our Gini index formula, and we're going to plug our Gini index formula into this first equation, and that's what we get. We get 10 over 14 multiplied by 1 minus, and then 7 over 10 squared, because that's medium and low for Bai's computer, yes, minus 3 over 10 squared, which is medium and low for Bai's computer, no, plus, and now we're looking at data space 2, D2, 4 over 14 multiplied by 1 minus, and then 2 over 4 squared, which is high and yes, minus 2 over 4 squared for high and no. That result gives us a Gini index of 0.443, which is also the Gini index that our income could be an element of high in our data space overall. We perform the same calculations for the constellation of low and high and for medium and high. And we find that our Gini index for low and high is 0.458, and our Gini index for medium and high is 0.450. This means, since we strive for our Gini index to be as small as possible, that our split on low, medium, and high has an optimal Gini index of 0.443, because that is the smallest number. It's smaller than 0.458, and it is smaller than 0.450. The second major method for optimizing the split attribute is information gain. We'll look at that next. Information gain measures by how much an attribute reduces the entropy, that is the randomness of class assignation before and after the split in the decision tree. Let's see how this plays out in our sample data set here. For that, we need to calculate our PI, that is the probability that any of our tuples here belongs to our class CI, that's Bai's computer no or Bai's computer yes. Then we calculate our expected information, that is the entropy that we need in order to classify any tuple here in D. For that, we are going to use this formula here, our expected information formula, which is minus the sum for all of our objects of all the probabilities that our objects belong to the class, multiplied by the logarithm to the base of 2 for all those probabilities. The reason why we're multiplying with the logarithm to the base of 2 for all those probabilities is that our information gain later on will be expressed in bits. So that helps us convert that. All right, let's plug our numbers in. So our information gain for our data space here, D, is the information for 9 yeses and 5 no's. That means in our formula that we have minus 9 over 14, that's our yeses, multiplied by the logarithm of the base of 2 of 9 over 14, minus 5 over 14, those are the no's, multiplied by the logarithm to the base of 2 of 5 over 14, and that gives us an expected information, that is an entropy of 0.940 bits. That's what we're starting with. Next, we're going to calculate the information needed after we have used our attribute to split our decision tree for classification purposes. So for that, we're going to use our information needed equation. that shows us the sum of all our settings here of the attribute settings in their own space versus the overall space, multiplied by the overall information for that attribute in its space. Here's what that looks like in our age attribute. For our under 30 group here, we have 2 yeses and 3 no's. That gives us 5/14 plus, and now we're looking at the 31 to 40 age group. We have the 4/14. You know, it's always good to have a frequency table like this one here. 4/14, and here we have 4 yeses and no no's. That's good. Plus 5/14 for our over 40s here, and we have 3 yeses and 2 no's. So that all comes out to 0.694. Now we can calculate the information gain, which is the overall information that we have calculated as 0.940 previously, minus the information that we have just calculated, the 0.694. That is the information gain if we split our tree on our age attribute, and out comes 0.246 bits. Now, if we perform the same calculation for income, or for student, or for credit rating, we're seeing that the results here are smaller than our 0.246 bits that we have calculated for age. This makes age the optimal split attribute for our tree because it is better with information gain. Remember, bigger is better. So far, we've used categorical attributes in order to calculate our information gain. This can also be done for continuous valued attributes. For continuous valued attributes, we typically use the midpoint between each pair of adjacent values, and that could be the possible split point. So we are looking for the midpoint between the values of AI and AI plus 1. And then we look for the point with the minimum expected information requirement, and that becomes the split point. Now, is looking at our decision tree through the eyes of a Gini index or information gain kind of complicated? Yeah, it is. Is there an easier way? Kind of. We could also use our decision tree in order to generate a series of rules. These rules would be if and then statements, but then again, each attribute value pair along our path would then form its own if-then statement, and with a complicated tree, that can very soon become a long list of if-then statements. But again, rule extraction is another possible vantage point from which we can look at our decision tree. To summarize then, we have learned in this module how to explain attribute selection issues. And we have done a whole lot of attribute selection by hand. We have computed the Gini index, we have computed information gain, we have seen how rule extraction could be a potential third way to look at a decision tree. But really, automation and programming seem to do a much better job than we can do by hand. Thank you so much for watching, and I look forward to seeing you again in a future module.